So in this next lecture, we're going to talk about the stresses acting in a beam. It's mainly a review of mechanics of material, strength of materials, and maybe just expanding on it. In this particular topic, what you know from your mechanics of material is that your stresses acting in the bar in a beam because of your axial load, okay, uh, is nothing else than sigma equal to nxx divided by the area, where the area is the area of the cross section. So if you would, this whole area has a cross-sectional area of A. And then also we know that if you have a cross section, right, and this cross section has a moment like this, then in this particular case, we know that your stresses are going to look something like this. Okay. So where this is the neutral axis, this is the neutral axis. For most of the problems, the neutral axis is the half of this, but not necessarily all the cases. And we can see immediately that this side is in tension, this side is in compression. So when it's in compression, we will write it as M C over I. Let's call this C1. The distance from the neutral axis here is C1, and this distance call it C2. Then this sigma would be plus MC2 over I. Or we can also write this in a different way. Put the minus sign because this is in compression, plus this is in tension. M over Z1, we can call this M over Z2. This is sectional constant. I provide those constants in your book, in my notes, in page 324. Those are my handwritten notes that actually I included on the website. And what we are really interested here are these values over here. And you can see that you know what your Z looks like for your common cross sections. Typically, many cross sections that we work with are these right here, these three. And so those are the ones that we care for. However, if we had a trapezoid, in the case of a trapezoid, as an example, you have no other choice than finding the I and dividing the I by either C1 or C2. So you don't have a closed form solution for that. So this is the Z, is called the section modulus, okay? This is called the section modulus. And we're going to solve many, many problems using that. Okay, so the next topic that the other stresses that we use a lot are tau is equal to V over A effective. Okay, for our terminology, this may be Y, maybe Z, depending on the direction that's applied, and we will talk about the subscript for this in a moment. This is a typical cross-section. So in here, you can see that your area effective for this particular case is 2/3 of the cross-sectional area. Here, the area effective is equal to 3/4 times the area. Here, the area effective for this case is nothing else than A divided by 2. Here, the area effective is the area of the web. So these are the common approximations that we do, and many of these actually not even approximations, they're stacked closed form solutions. So this is V over A. And one thing that you have to keep in mind when you're solving this, that when you do V over A, this tau actually acts all the way along this. And so you're talking about a shear load that actually does that. However, when we take this approximation, we are assuming we are taking the average. Um, so what we are doing is we are basically taking the average of the whole shear load and saying this is all over V. Okay, so this is V over A. That's the only reason we can possibly do that. Otherwise, you have to use the VQ over IT, this formulation. However, for many, many engineering problems, the approximation to this, to be effective, is good enough for the problems that we solve. Okay, so the other stress that we use a lot is torsion. Torsion, again, you are very much familiar, is TC over J. Uh, However, another way that we use this a lot is T is equal to T over Q. And now is this going to be plus or minus, but we will talk about that in a moment, including the subscripts here as well. And the Q again is given by the table that I provided in my notes. And these are the typical cross sections for the nodes. Just be careful of this. This is 2 times A, and this is 2 times B. So if you have a cross section where this is A and this is B, you have to take half of that. That's what goes inside here. It's the half of that distance. Okay, just have to be cognizant of that. Okay, so these are the stresses, typical stresses acting on a beam. And one of the things I wanted to talk about now is how the stress is acting in a cross section, a typical cross section of a beam. Okay, so again, just to remember this, so let's suppose we have a beam has some loading conditions, right? And uh, uh, we got different boundary conditions, and we got loads, we got moments, we got all sorts of stuff happening there. We always identify a critical location, right? The first thing we want to do in the problem is identify where X critical is. This comes from your shear moment diagrams. Typically, as I told you, this is just as a review, your MXX, MZZ, MYY are the drivers. Okay, I'm not ignoring the shear, maybe important in some few cases, but mainly these are the drivers for selecting that. Now, at that particular critical location, let's suppose, just for the sake of this discussion, is a circular beam, beam of a circular cross section. So you have a beam that looks something like this. Okay, at this location. Okay, so this is the location X critical. Now, in that location, we're going to put 5 points. Okay, point A, point B, point C, point D, and point E. Now, we want to see what happens at each one of these points in detail. We know that for a positive, if I look at the cross-section seen from this side, this will be your Y, this is your Z, and your X goes upward. So this is Y, this is your X. What we know in the problem is this is my positive moments, your V, and you have your axial load, and also you can have a torque, right? So we know that. So what we're going to do is we're going to study what happens for each one of these cases, 1 point at a time, and see what happens with them. Let's start with the case of axial load. Axial load is quite easy. So what you know for the axial load, when you're solving these problems, and I look from the side, I have an axial load applied. Uh, because of my Saint Venant's principle, I can assume that if I make a cut, all my loads are my stresses in my entire cross section are symmetric. Okay, they're identical. So that means that the amount of stress acting in each one of my points at my point, each one of these points will be the same value. Okay, so point A, point B, point C, point D, point E are going to have identically the same value. So I can say yours, that would be, now what subscript do I put, right? I have N over A. This is same value. So it's acting in the X direction, in the X plane, and it's acting in the X direction. So this is sigma XX. Again, just if you look at from this side is Y, this is my X, my coordinates. I can draw them here as well. I can draw my coordinates here. So this is Y, this is X, this is Z. And what we are saying is this value right here is acting in the X plane, which is normal to the X in the X direction. That's why this is, and this will be positive, assuming there's a positive load, okay? So all my points, if I was going to make a table, and let's make this table with point A, B, C, D, and E. So my sigma XX, pick up my axial load, okay, let's call this axial. This is axial load. In all the points is sigma XX A for axial, sigma XX A for axial, sigma XX sigma XX sigma XX This is for axial. Again, this small script A, we can go here and I'm placed this A. This is for axial. That's what we mean, this axial load. Okay, so, and they're all positive, assuming that your N is bigger than 0. Okay, this is assuming that your load is bigger than 0, right? It's not going in the compressive direction. So this is what the axial load is going to look like. So let's move on to the next type of load. The next type of load is the let's work with the bending load. Now for the bending, I have a load applied. Let's assume this is my positive M. Okay, and because of Saint Venant's principle, I can show that my load variation looks something like this. Okay, so note that here, this point right there, there are no stresses. Okay, there is no stresses because of bending. This is at the neutral axis. Okay, so what you're saying is no stresses at neutral axis. Okay, so if I take now my cross section, and you can see that this is going to be in compression, this is going to be in tension. If I take my cross section now and I put my 5 points, it should be clear that my point B, my point D, my point E, they all lie on this point right there. You see? So you know that in this location right there, there are absolutely no stresses. Okay? So your stress is actually equal to 0. Now, in this point here, you know that your stresses are in compression. This point, your stresses are in tension. And again, if I want to know what is subscript this is acting, it's a stress acting on the x plane, because this is my x plane. It's acting in the x plane, is acting in the x direction. I'm going to use B for bending. Okay. And then what you're going to do is here you have, this is equal to m over z. Okay. This is plus, no, sorry, this is minus. This is minus sigma xxb because it's in compression. This is plus sigma xxb because this point is in tension. And so all we are doing is evaluating what happens at those 5 points, at point A, at points B, C, D, and E. And we see that in bending, in the case for bending, this is 0 and this is maximum at the top and at the bottom. One side is going to be in tension and the other side is in compression. Okay. So if we did this, now we can go and fill the table again, and you can pause the video so you can create these tables, bending. And we saw from the problem that this was minus sigma xxb. This is 0, this is 0, this is 0. This is plus sigma xxb. Okay, this is assuming again that your moment is positive. If it was negative, then obviously everything flips. Now, the next thing we're going to do is we're going to work with shear. The shear load, again, we know the actual shear distribution for V positive. Okay, your shear distribution looks like this. But we know there has to be 0 at the bottom, at the top, and maximum in the middle. And we talked about this being tau equal to V over A effective. Okay, so if I was going to do this now, draw this in my cross section, point A, B, C, D, and my point E, what you can see is that at point A, my tau is 0, and point C, my tau will be 0, because at the your shear stress distribution looks like this, where it's 0 at the upper fiber and the lower fiber, and it has to be maximum here in the middle. So in the middle, all my values have V over A effective, okay? And then the value that you will use your subscript will be as follows. It's acting in my x-plane, so it acts in the x-plane, but it acts, now is V, so it's acting upwards, right? So it's acting in my y direction. In this case, they're all acting positively, right? They're acting upwards because the same value for each point is going to have identically the same value. So if I go back to my table, and now I keep adding to the table, and I say shear, okay, is tau xy, and I'm going to V as in shear, sorry, is 0 here, 0 there, is plus tau xyb plus tau xyb plus tau xyb. This is for V positive. Okay. Again, you just have to evaluate one point at a time what is really happening. Now, there's one more point that we have to consider. One more loading condition is the torsion. Now, torsion can be a little bit more trickier, so I'm going to draw the cross section. Point A, point B, C, D, and E. And you can see that for a positive torque acting in this direction, T, this is my T positive, but it's going to, my stress experienced here is in this direction. The stress here experienced is this, but then it's zero at the middle. This is zero. And all these stresses are nothing else than T over Q. Now you have to watch out. Let me add our axis. This is the z-axis. This is the positive. This is my positive y-axis. Okay. So what you have to keep in mind is the direction. This is still acting in the x-plane. Remember, x goes inboard, outboard. So it's acting in the x-plane in the z direction. Okay, put the letter T for torque, and it's positive. Why? It's acting in the positive direction. Here is acting in the x direction because it's the x surface, but it's acting in the y axis. He's acting in the y. And this is torque, but it's minus because my y goes positive upwards. Here, my tau acts in the x direction, x plane in the z direction, but it's negative. Why? Because it's in the opposite direction. It's going in this direction. Here, this will be tau y torque, and it's positive. And all have in the extreme fiber for a circle will have the same value, T over Q. Okay, so if we did that and we went and we tried to fill the table now, for this particular case, what you can see is I have torque, and at point A, it was plus tau xz torque. You can see it from here. It's positive. See, xz is positive. Then you have in the B, you have minus tau xyt minus tau xz torque plus tau xy torque, and then you have 0 in the middle. These all values come from doing a free body diagram, what happens to torque. Again, this is assuming a positive torque. If it's going in the opposite direction, all the directions change. Okay? So summarizing all these thoughts, just fixing these thoughts now, let's see what happened, what conclusions can we draw. For point A, what do we know? We know that point A, this is my point A. I know that my bending is going to be maximum. It's going to be critical. It's going to be minimum. But it's negative. I know that my axial load is going to be the same. I'm going to have torque, but zero shear. Or let's write it down right here below this table. We know in this particular case, here we have 0 shear, minimum bending, max axial, and max torque. Okay, all this happening in this at this point right here. Okay. At point B, we can see is that we have max shear, but we have 0 bending. We have max axial, and we have minimum torque. These values right here, minimum minimum, maximum, really, they're sign dependent, right? Because if it goes the opposite, this become max, become minimum, and this become max then. So we many times treat them as critical values. And then point C is basically it's very similar to this. I have zero shear. I have max bending. I have max axial load. And I have minimum torque, but it's actually maximum torque, right? The values are the same. What's going to change is just the sign. That's why I put a minus sign there. Here, this point right here, we know that we have maximum shear. We know this is zero bending, max axial, and max torque. Okay, this point, note that can never be critical. This can never be critical. Never. Why? You can see I don't have any of the moments. This is the only point that doesn't have any moments associated, so it's not even worth to check it. Okay, has zero torque, zero bending, maximum shear, and maximum axial load, but doesn't really say much. Okay, so with this said and done, I am going to do the following. I am going to just give me a sec. I'm going to use this point. Okay, this is what my stresses are at that point A. Let's build our stator stress. Your stator stress for point A will be nothing else than sigma xx A minus sigma xx B. This is sigma xx. The total thing here is sigma xx. So I have to add them up. I add this plus this. I don't have any other stresses, axial stresses. I don't have any stresses here. I don't have stresses here. I only have one stress plus tau xz and its torque. Tau xz and it is torque. Okay, so this is my point A. And then I want to do point C right here below this. I have a purpose for that. So let's go back to my table. Let me take my point C. And again, remember, this right here is sigma xx. So my stator stress for my point C then will be sigma xxa plus sigma xxb. The axial and bending get added up. These are all zeros. And this is xz, that's minus tau xz torque minus tau xz torque. Okay, and this is 0. That's point C. Let's go to point B and point E. Point E, let's build them all just as a practice. So now we go to point B. Okay, point B is going to be, just give me a sec. This is my point B. So when I do my point B, I see my point B, stator stress at point B will be sigma xx axial plus tau xy minus tau note that these are y, right? So these tau xy get added up. So it's minus tau xy torque, tau xy due to shear load minus tau xy due to torque, and everything else is 0. Okay, and then my point D will be, so as you can see, the secret of this problem is to fill this table. You fill this table correctly, and then everything else falls in its place. Okay. So now we come here and just note that got y and y. Since it's y and y, I will add them up. This is at point D. We'll have sigma xx axial, tau xy due to shear plus tau xy due to torque. This is 0. I don't have anything else acting here. And this is symmetric. So this is your state of stress for the main points that we are under consideration. And just for completeness, your point E will look as follows, will be as follows. Okay, so this state of stress, E, is going to look like, this is EXX, A, tau xy v is all positive, everything else is 0. So this is the state of stress at point E. And now if we evaluate all these state of stresses now, let's put them all together in one chart. So I take out all my state of stresses and put them together in one chart. Everything comes from this. You just have to be systematic and say, hey, what happens to my axial? Hey, you may have minus 100 pounds. Okay, then you put minus 100 points in all points. Sorry, not pound, PSI or KSI. And maybe this is minus 1200 KSI. Okay, then put minus. Then if it's minus, if you find that your load is negative, then this will be plus, this will be minus. You have to do your free body diagrams like this. If this happens to be a torque of minus 1200 or minus 1200, okay, then it goes in the opposite direction. That means everything is opposite. That means now it acts in the x direction on the x plane, but in the opposite z direction. So now instead of plus, it will become minus, negative. Okay, so once you build this, the question is, which of this is my critical state of stress? So let's evaluate and see what's going on here. When you see this, you're going to realize that, wait a minute. First of all, remember, I care a lot for my bending, and I care a lot about my torque, because these are my big drivers. This is M over Z. This is T over Q. So here you see from all these state of stresses, my point E, and if we draw this circle just to have it, A, B, C, D, and E, what you can see is the only point, is exactly the only point here that actually does not have no bending stresses. So I know immediately these terms are included here, here, and so this one at least has the torque in it. This one doesn't even have it, so I know this cannot be a possibility. Now, if I compare these two, first of all, they're basically identical. Yeah, you might say I have a minus sign here, I have a plus sign there, right? You might say, well, what do we do with that? I got a minus and I have a plus. Well, ignore that. It doesn't matter. They're independent. They're not being added to anything. However, when you compare this term with this term, you can see here we are subtracting, they are adding. So this term is going to be higher than this term. Okay, for this particular loading condition, obviously point C is your maximum load. It is critical. When I compare these two, the same logic, the problem is almost identical. I got axial, I have axial. The only thing difference is these two values. Here the values are subtracted, here they are added. So this will be still bigger than this value. We end up with these two state of stresses. Now, here I have the same value torque. Remember, it's the same value, T over Q. So I have between this point and this one has the bending stress. This one does not. Then what I would say in this problem, this is my critical point. Okay, so this is the state of stress that is critical at X critical. Okay. That's how we actually do these problems. We are mainly interested in trying to find the whole purpose of these problems is trying to find which all we want to do is try to find at what location, what point is my design point. The design point will be the point in which your moments are maximum, and that particular point in the cross section gives you the maximum, the critical state of stress. So when we did this, and go back, we did this, we started the problem. I just want to review again. We did this, we found what your stresses look like. I told you what your Z's are. I tell you what your Q's are. And then I'm going to start filling in the blanks, okay? Then I start the axial load. Axial load, I know in this case, assuming that N was positive, then for N positive, this gives me all positive values. Then I go with my mole bending. Bending was negative at the top and positive at the bottom because of my reaction. You see, I'm applying a load. So this fiber, outer fiber is in tension, the lower fiber is in tension. It's in compression at the top and in tension at the lower fiber. Then when we do this, that's why I put a minus there and a plus there. At the neutral axis, we don't have anything. B, E, and D are at the neutral axis, by the way. Then we move to the shear. And the shear, what we did was we noticed the V over A has to be 0 at the top, 0 at the bottom. So we just use V over A. I know that in some authors just want to bring this up. Since we are using V over A, they have a approximation saying, hey, let's take V over A at all the points. If you want to do that, you can do that. You can. That's not going to change your answers, because remember, your shear is not a driver, unless that's the only thing you had in the problem. In such a case, yes, then you might have these values at A and B as well. Then you went with torque. We know that this is the value of the torque. This is how it is. And then we just place what the direction of the stresses will look like. And we build the table. And then we analyze what happens at each one of the points in the table. Once we have that, then we move and we combine all the axes together, any other terms together, and we build the state of stress. Once we have all the state of stresses built, then we want to go ahead and analyze and see which of all these state of stresses is the critical one. Okay, and sometimes another option that you could do is you could take all the state of stresses. Okay, you could take all the state of stresses. I am not going to put the point B, E, because we know that. You can find where your sigma, your maximum stress is here, maximum stress is here, your maximum stress, and you could just compare them. But that's not a very good way of doing that, because then you might be compression sensitive. The problem might be, sorry, this should be B, C, D, because your problem might be compression sensitive as well. So another alternative to this problem is ductile material use von Mises stress, but we will discuss that later. You could use von Mises, but I will discuss this in a further class. So this concludes the topic on stresses acting on a beam and what the state of stress looks like.